the microphone is necessary.
Afternoon session, Ilias Diakonopoulos will give us a tutorial on algorithmic high-dimensional robust statistics.
Thank you, David. So I'd like to thank the organizers for inviting me to give this talk. It's going to be a tutorial on some basic things and some recent developments on algorithmic robust statistics for high-dimensional problems. Okay, so let's begin. So this is the question that we're going to try to answer. So can we develop learning algorithms that are robust to a constant fraction of corruptions in the data? So imagine that we have high-dimensional data, the dimensionality increases, goes to infinity, and we still want our learning algorithms to be tolerant to a fraction of corruptions that's like 10%. It doesn't go to zero when the dimension goes to infinity. Now, this is a classical question in statistics, so the field of robust statistics is quite old. So there are three motivations that I will talk about for a couple of minutes for you to get used to my voice. The first one is the classical one of model misspecification. So even in the 20s, when Fisher wrote his first paper on parametric inference, he realized that the assumption that your data come from the model that you assume, from the family of models that you assume, is an unrealistic one. So we really want algorithms that do not overfit to this assumption of coming from the model, because even in the best case, the model is going to be approximately valid. So this is the classical motivation, and two sort of practical fields where this type of stability of algorithms is important is when you have real data sets, for example, biological data sets. There are real outliers in the real data set, so you want to detect them and remove them. So my friend Petros Dryneas tells me that this is a big issue in biology, particularly in population genetics. And the more modern type of motivation, so can you see them? You can, right? Okay. So is from a field that's called adversarial machine learning. So there is a type of attacks on machine learning systems that are called data poisoning attacks. It's like a nice name. And this line of work introduced by Bigio et al., which basically corresponds exactly to this setting of having a small fraction of adversarially corrupted data. So let me tell you a little bit about these two fields. So the first one is, okay, we know that high-dimensional data sets are inherently noisy, and this has been observed in various biological settings. So one of the critical problems that the domain scientists have there is that it's very painstaking to actually detect those outliers. So we'd like to be able to do this automatically and ideally with provable guarantees. But the problem is that the data is very high dimensional, so we cannot just eyeball the points and see which are outliers and which are not. And this is slightly different than the setting of having adversaries. So here, the outliers, the points that are different than, let's say, the majority of the points, can actually be useful. So you don't necessarily throw them away once you find them. You may need to look at them. Okay, they actually might represent something about the phenomenon you're trying to explain, which you didn't know about. Okay, and the second one is this data poisoning thing that I mentioned. The classical example is fake reviews in Amazon. So the idea is as follows: you have a machine learning system. Usually the data comes from outside, from a bunch of users. So some of them might actually be fake. Or adversarial. They might want to convince you that some product is good, even when it's not. So whenever you have a recommendation system, whenever you have a crowdsourcing setting, this is a big issue, because at the end of the day, the way the system works is that it gathers the data from all the users and runs some machine learning algorithm. So if this algorithm is not stable, it can actually be corrupted very easily with a small fraction of adversarial corrupted data. This is a problem. Okay, you get completely incorrect recommendations, etc. So then let's start with theory, which is the reason we're here. So what is the definition of the statistical learning problem we're going to look at? So for most of this talk, I'm going to talk about unsupervised learning, but this is sort of more general, and the techniques I'm going to talk about apply more generally. So the setting is as follows. Statistical learning setting. So there is a sample generated by a statistical model with unknown parameters. Let's say the unknown parameters are theta star. And the goal is to estimate the parameter, this theta star, find the theta, which is approximately theta star in some sense, given access to samples. So as computer scientists, really the thing we usually ask is there an efficient learning algorithm, computationally efficient for this problem. However, there are more than one criteria to look at. So the sample size, so how many samples you need in principle to be able to estimate theta star is what the classical statistics looks at. The running time is what we have been looking at, and robustness is something that I'm going to talk about today, which means basically, okay, what if the samples do not come from the model, come from approximately the model, what can you do? So the more refined version of question 1 is, are there inherent trade-offs between these criteria? So is it always possible to minimize these 3 criteria at the same time or not? If we're able to do this, it would be great. And in fact, we'll see that we can almost do this for some basic sets, but not quite. Okay, so I've talked about robustness. It's a very general phenomenon, so let me define what I mean in this talk by robustness. So the model of corrupting data is as follows. So there is some known family of statistical models. For example, this could be all high-dimensional Gaussians with a known mean and covariance matrix, or all mixtures of Gaussians, or you name it. And now the process is as follows. First, we generate a number of samples from a distribution in that family. Okay, so we have an all-honest set of samples, let's say capital N, and then an adversary who has access to this set of samples can arbitrarily corrupt an epsilon fraction of them. So epsilon is basically a number between 0 and half, so less than a half, that quantifies the power of the adversary. Okay, the adversary can corrupt 10% of the samples, so probably less powerful than someone who can corrupt 20%. So this is the definition of the contamination model. It is very related to an old model from robust statistics, which is called Huber's contamination model. In the next slide, I'm going to explain what this means. Now, the goal is, given an epsilon corrupted set of samples from a family of distributions, learn the family. Learn as well as you can, with few samples, polynomial time, and as good accuracy as you can achieve. All right? So that's the, yes, Ken.
So in the case of supervised learning, an adversary might mislabel things. Is that contained in this model? Or
yeah, of course. So a sample is not necessarily an unlabeled point. It could be x, y, where x is the unlabeled data point and y is the label. Okay, so yes, this contains supervised learning as a special case. Yes?
We assume that we know script F?
Yes, yes. So we know what family we're trying to learn, which, the model selection problem would be even harder. All right, so now let me be a little bit more specific about the models and what the adversary can do to the data. So there are 6 different models in these slides. So basically the adversary can have like a lot of power or even more power. So there is a difference between oblivious adversary versus adaptive adversary. So oblivious means that the adversary cannot look at the samples, the good samples, before they corrupt them. Adaptive is the opposite. And the second difference is that the adversary can only add corrupted points versus both adding and subtracting. So you can look at your good data, adversarially subtract, let's say, an epsilon fraction of them, and then adversarially add another epsilon fraction of them. So this would be the strongest adversary. So now you get 6 possibilities based on the combination of these things. Now, the one we're going to talk about is the one here, the strongest one. So the adversary is adaptive, can both add and subtract. And the Huber contamination model is the weakest one, where the adversary can only add an epsilon fraction of corrupted data, and literally the noisy distribution is the mixture, which is 1 minus epsilon good distribution plus epsilon some fixed bad distribution. Yes?
So in all these models, the corruptible samples are not randomly picked. That is not the case that every example has probability epsilon of being corrupted.
No. The adversary can choose any way to. Yeah. So is the setting clear? Yes.
But I thought that was, I thought that was equivalent to the oblivious model because the adversary can't see the other points, so its choice of which to corrupt are effectively random. Is that not correct?
So what I mean by oblivious adversary is this. It means that the data is going to be drawn from a distribution, and this distribution is going to be 1 minus epsilon times the good distribution you're looking for, plus epsilon times the bad distribution that is fixed but arbitrary. While in the case of the strong contamination model, you may not even get, your data may not even be drawn from a distribution. They're not necessarily IID from a distribution. That's the difference between the two.
So, so in the oblivious adversary might know the distribution it's being drawn from, but it's,
Yes, the adversary knows the distribution but hasn't seen the samples.
but it's not able to say, draw a bunch of samples, take the largest so many, and then corrupt those further.
No,
Right,
no.
okay.
Yes.
Also, I'm still confused. You said epsilon b, so it's assumed the perturbed or the corrupted samples are drawn IIT from a particular distribution.
Yes.
Is it?
Yeah, and this distribution,
Not really adversarial, totally.
I mean, the distribution here can be fixed but arbitrary. So the adversary
The
can choose.
IIT samples from B.
Yes, yes, yes. Yes?
So Huber's contamination model is a mixture model.
Yes.
The subtractive oblivious model, there's a minus sign. What does that mean?
You can put the minus in the other sides, and then it means that basically you have a mixture. Okay, it means that your actual distribution at G is going to be a mixture of two things. Okay, so let's not belabor too much on these models, because at the end of the day, for most of this talk, I'm going to be using this one, and everyone understands what this one means. So these are the definitions of the models, and we're not going to distinguish too much between them until the very end. Okay, so let's move on. So let's start with one dimension. Okay, so you all know how to learn the mean and the variance of a Gaussian. Okay, so this is the standard parameter estimation. So there are no corruptions here. So we know how to do this. Okay, so if you output the empirical mean and the empirical variance, these are going to converge to the true mean and the true variance. And these particular estimators are a special case of something you all know, the MLE that Fisher developed, and we heard yesterday that it has these good asymptotic properties. Unfortunately, though the MLE does not work in the setting that I described, in the corrupted data setting, and this is not a matter of computational efficiency or sample efficiency. It does not converge to the right answer. Okay, we're going to see that very soon. And this is a question that Tukey asked, like in the 60s. So what happens when you have errors in the model itself, when the model is misspecified? How do you actually learn? What should be your method? So one historical point, I mean, I guess you all know Fisher, because he developed the maximum likelihood estimator and many other things. You should also know Tukey. He developed the fast Fourier transform, and he was actually interested pretty much in computing. He was a mathematician, but he was interested in computing. He coined the terms bit and the term software when he was working at Bell Labs. So that's what Wikipedia says. So he was a very computational friendly mathematician from that time. So now the field of robust statistics started with this paper, essentially. This is the thesis of Peter Huber in the 60s, who got his PhD from here, from Berkeley. So this is a field that has existed for a while, and the major sort of complication here is that the algorithms that statisticians had did not scale in high dimensions. So the question was, can we avoid it or not? So we'll see that very soon. So we saw non-robust estimation in one dimension. Let's look at robust estimation in one dimension. So we know that if we have corrupted samples from a one-dimensional Gaussian, then we still can efficiently, accurately estimate its true mean and true variance. Of course, we cannot use the empirical mean and the empirical variance, because even a single corrupted sample can completely skew these estimators, so they can become completely unbounded. But Statistics 101 tells us that we can still use the median of the samples, and the median is going to be a robust estimator of the mean in one dimension. And also for the variance, there is something which is called interquartile range that has similar properties. So let me show you a folklore fact. Suppose that we get a set S of n epsilon corrupted samples from a one-dimensional Gaussian with unknown mean and unknown variance. Then the median of the set S satisfies this inequality. So it's absolute value of the difference from the true mean. Okay, so this is the mean of the distribution before the corruption, not the mean of the distribution that you observe. Okay, it's going to scale as epsilon plus something that depends on the samples times sigma. So that's the right normalization. So we know how to do that. So the median is a robust estimator of the mean. It gives you essentially the optimal accuracy that you could expect, and it is computationally easy to calculate. So what happens in high dimensions? So this is the question we're going to explore in this talk. Is the setting clear? So one thing I want to say that is going to become apparent later is that when we have no corrupted data and your sample size goes to infinity, your accuracy goes to 0. Okay, that's what we all know for the MLE, etc. This is not going to be true in the robust setting. In the robust setting, when you have an epsilon fraction of corrupted data, even if you get your sample size to be infinity, your error is going to be at least epsilon, or epsilon scaled. So this equation here is not a coincidence. So even if n goes to infinity, we're never going to be able to get error 0. And really, when n becomes 1 over epsilon squared, these two terms are the same, and usually we take the sample size to be that. Okay? Now, what happens in high dimensions? So the question we're going to look at, yes?
So what if you wanted non-constant failure probability?
That's fine. Everything works. This is for simplicity here. You can get basically log 1 over delta, as we all know for these settings. So the sample size, so this is, you can basically with 1 over epsilon squared log 1 over delta many samples, you can get the same thing. Okay?
Is that the best known in one dimension?
Is the best known, the best possible?
Well, whatever you like.
What's the question?
Best possible.
The best possible is 1 over epsilon squared log 1 over delta samples, and it gives you accuracy epsilon times sigma. Yes?
It's best possible up to like constants, right? Because you can. I thought you could do better than the median, like better constant factors than the median.
In fact, in one dimension for the Gaussian, the median actually gives you also the optimal constant, which is square root pi over 2. If you want to know, for high dimensions, it's unclear. Okay. Okay. So let's go to high dimensions. So that's the basic problem we're going to study throughout the talk. So I get a set of epsilon corrupted samples from a Gaussian with identity covariance and unknown mean. Okay, so this is the distribution before the corruptions take place. The covariance is known to be identity, the mean vector is unknown, and what I want to do is to recover an estimate of the mean within a constant times epsilon. So I'm not going to belabor too much what the constant is going to be as long as it's universal. In fact, we're going to see that in some cases even a constant is not possible. So again, epsilon is a fraction of corruptions, a number less than a half. And this is what we want to do. So why do we care about L2 distance? Well, if you take two Gaussians with identity covariance, their total variation distance is proportional to the L2 distance between their mean vectors, at least when that is small. So basically, by getting a guarantee of this type, we get a guarantee, the same guarantee up to constants for the total variation distance. So if we're able to approximate the mean vector, we're able to approximate the distribution with respect to this global error metric. And again, the optimal rate of convergence here with n samples is known to be a constant times epsilon plus square root dimension over number of samples. So in one dimension, we had d equals 1. So this is the best thing you can achieve. So at the end of the day, I don't want to keep capital N everywhere throughout the talk. So I'm going to make capital N d over epsilon squared so that these two terms are basically the same. Okay? There is no reason to use less samples because the sampling error is going to be huge. There is no reason to use more samples because you're never going to be able to improve upon the first term. And now let me tell you what was known in robust statistics for this basic problem. One thing you can do is do some naive outlier removal, the points that are very far out, remove them. I'm going to actually show that in detail a little bit later. This is fine in terms of running time, but unfortunately, the error guarantee you're going to get, which is basically the first term in the previous slides, is going to scale like epsilon times root dimension. So when the dimension goes to infinity, this is essentially a useless bound because essentially we estimate the mean of a Gaussian which has essentially no overlap with the one that we're looking for. And this type of epsilon root t guarantee has been the plague for high dimensional robust statistics from an algorithmic perspective for a long time. You can try other things. You can try to take the median in every coordinate. And again, it's easy to calculate, but it has the same problem. The error is not going to be epsilon. It's going to be epsilon root d. You can try other variants of the median, which is basically the geometric median is the point that minimizes the sum of the distances from the sample sets. Again, you can compute it. Unfortunately, it also gives you epsilon root d error guarantee. And then we can go to robust estimators that are actually exponential time. So there is a generalization of the median in high dimensions, which I'm going to explain very soon. which gives you the right error guarantee. So this is called Tukey median. But unfortunately, in general, it's NP hard to compute, which means if I give you an arbitrary data set and I tell you solve the optimization problem that the Tukey median prescribes, it's an NP hard problem. It's NP hard even to approximate. Even the heuristics that people have tried do not scale. You have to assume something more about your data to be able to do something. And there are some other techniques from statistics that have the similar issue. They give you the right type of error guarantee, so theta epsilon error, but the running time is exponential in the dimension. Peter?
So it was just a question really about the previous slide and the implications here. So this assumption that n has this dependence on epsilon, the d over epsilon squared, doesn't. If you choose a bigger n, it's
no. Even if so, this is going to be the error guarantee that you get from these algorithms when n goes to infinity.
It's still
so even there is no sort of and the reason is that you have you get more samples, you have the same fraction of corrupted data. Okay. Okay. So that's the punchline. Yes.
What if instead of getting theta epsilon, I want something in between, like epsilon times d to the 1/4 or something? It is still.
So before we worked on this work, as far as I know, there was nothing better than root d, and in fact, this root d can be worse. There are problems where it's actually times d or even worse.
But the NP hardness, you said it's also for approximation. Do you mean constant factor?
I'm not sure exactly what the geometers would know that, like Ken would know that. But the point is that the Tukey median is not an algorithm. It's an optimization problem that in general is NP hard. So in principle, it doesn't tell you anything about how to solve the problem. Does it make sense?
Yeah, I was just wondering, is NP hard to approximate?
The best approximation algorithms, I think, have like a root d factor. Okay, that's my recollection. So you were looking at these problems historically in geometry for constant dimension. So n to the d running time was fine, or 2 to the d running time. But we're not in that regime. All right. So that's a punchline. Is there another question? So yes.
Do these hardness results also work if you're okay with order root epsilon? Things like that. I mean, would it really matter? Would it be fine if I had no?
So I'm not sure, because this is like literature I'm not an expert on, but I would assume that any function of epsilon would have the same impact. So that's a punchline. So this is where the talk should begin. That the known estimators, before the work I'm going to describe, belonged in one of two categories. So either they were robust in the sense that they give you an error which is close to the information theoretically optimal error, which is usually some function of epsilon independent of the dimension, but they're hard to compute, or there is the compute, but the error blows up. The error in the input is epsilon, the error in the output becomes epsilon times root dimension, or something like that, and therefore these algorithms can tolerate a negligible fraction of corruptions. So the question is, okay, can we achieve the best of both worlds? Can we get robust estimators that run in polynomial time? So I'm going to give you two answers to this question. The first one is what Peter Huber believed. So this is a quote I got from this booklet. So there was a first edition in the 70s and a second edition in 1996. I think the difference between the two editions is the first page and the last page. And in the last page, this is what he wrote. Okay, so I don't know how you interpret that, but one interpretation is that he didn't believe that there is generically a polynomial time, a low degree computational complexity for solving these problems. Okay? But the reason we're here is that in fact you can say something. So it is possible to get robust estimators that are also computationally efficient. And today I'm going to give you the very basic ideas of how to do that. In particular, how to get tolerance to a constant fraction of corruptions. And this comes with general methodology. And here it should say methodologies. I think I'm going to describe 2 or 3 different related techniques. So the meta theorem that has come out of this line of work, not only out of these initial papers, but there has been a lot of follow-ups, is that as long as your good data has some nice concentration, then you can design polynomial time algorithms that are robust and tolerate a constant fraction of corruptions. So that's the informal thing that you should remember. And the first 2 papers that made progress in this question are by these authors, and basically introduced 2 related techniques that I'm going to describe. Okay, so the paper had many results, like robust estimation of mean and covariance. The first one, results about robust density estimation for spherical Gaussians, mixture of spherical Gaussians, mixture of product distributions. The second one, independent component analysis and robust versions of SVD. But for this talk, I'm going to only state and prove this theorem. So the most basic setting. So this says that if we want to robustly estimate the mean of an identity covariance high dimensional Gaussian, then we can get error which is about epsilon. In particular, the work by LRV, so Lai, Rao, and Vempala, in the additive contamination model, the model where the adversary can only add corrupted zeta, so this is an adaptive adversary, it gives you an error which scales with epsilon times square root log of the dimension. So the square root dimension became square root log of dimension, so this is almost constant. And in the strong contamination model, where the adversary can both add and subtract points, this work by Kamath, Kane, Lee, Moitra, Stewart, and myself gives an accuracy of epsilon times square root log 1 over epsilon, so completely independent of the dimension and almost linear, but not quite linear. We're going to see hopefully why. Now I should say that this is how these papers were written. If you in fact tweak a little bit the first algorithm by using some lemmas of the second one, you actually get that even the first type of algorithm is robust in the strong model, but you need to multiply the accuracy by a square root log. Okay? So that's the statement we're going to try to prove. So before I do that, so this is I think a good point for questions. So before I do that, there is a bunch of introductory stuff I want to get out of the way, and then I'm going to present the ideas for these algorithms. So are there any questions?
So I don't understand this adaptation statement at the bottom. You're saying the second.
Oh, can be adapted. Can be adapted. It can be modified.
Sure, but the second theorem seems to be in a stronger model of error.
It is. Yes.
And so why don't we just get the minimum of the two errors then, instead of getting something which is worse than both?
The statement is for the first one. The star is in the first one.
The star is here.
These are two different algorithms?
Yes.
And you're saying the first one you can also get something for the strong contamination model?
Yes. Which is basically essentially the same up to the square root log. Is it clear now, Madhu? Okay, so the star was here. So, okay? Okay. So let me, these details I think are going to be either not important or they're going to come up later and I need to explain them. So here is the structure of the talk. So part one is over. I'm going to start with some basics. I'm going to tell you what's the sample complexity of the problem, how do we get a robust estimator if we don't care about running time with a few samples, what is this naive outlier removal and why does it work. And then after that, I'm going to give you an overview of these approaches at a very sort of high level, how they relate to each other. And then I'm going to describe explicitly what each one of them does. Probably the first hour is going to be up to here, and the second hour is going to be the rest. All right? So that's the plan. So let's start with some basics. Are there any questions based on this slide? I hope not. Okay? So, okay, question number one. How do we learn the mean vector of a Gaussian without corruptions? Okay, so we have d dimensions. And we're going to estimate within, let's say, L2 norm delta. Then the answer, the number of samples that you need, is dimension divided by accuracy squared. Okay, that's the answer. It's an upper bound, it's a lower bound. If you have never seen that, this is statistics like 101. Let me show you how you do this. Okay, it's easy. So the empirical mean, what is it? You take all your samples and you divide by the number. Okay, it's the average. And we know what the distribution of the empirical mean is because we know what the distribution of each sample is. There's going to be IID samples from a Gaussian with a known mean vector and identity covariance. So the empirical mean is going to be a Gaussian with the same mean vector, and the covariance matrix is going to have variance like 1 over number of samples times the initial variance. So it's going to still be diagonal, still you have independent coordinates. So let's calculate the expected L2 square error, just the sum of the expectation of the squares. But now, what is this quantity here? Since we know that mu j, the ith coordinate of mu hat j, the ith coordinate is a Gaussian with mean value mu j and variance 1 over n. So this quantity here is the variance of that, right? This is the variance of mu hat j, and the variance of mu hat j is 1 over n. So I sum these d times, I get d over n. So the expectation of the L2 norm is just at most the square root of the expectation of the square. So at most square root d over n. So Markov's inequality tells us that if you take the number of samples to be dimension divided by delta square, with probability at least 90%, you get error L2 error delta. All right, that's a basic argument. And if you care about high probability, all these things are well understood. Now, what is not entirely obvious, but it is true, is that you cannot improve on that. So any other estimator for this problem is not going to beat the empirical mean up to small constant factors. And there is a standard minimax method in information theory to do that. You cook up a family of distributions such that learning an arbitrary distribution from this set or a random distribution for this set requires many samples. I'm not going to explain that, but this is basic. If you don't know it, you can open any book on minimax, like Tsibakov's book, and find this stuff. Okay, so d over delta square up to a constant is also an information theoretic lower bound, so the empirical mean is the essentially optimal estimator in this setting. So that's basic thing number one out of the setting, out of the way. So the second thing I'm going to argue is that even in one dimension, in the robust setting, so now we're moving in the robust setting. In the previous slides, we're about learning a Gaussian without corruptions. Here we're going to argue that learning a Gaussian even in one dimension, with an epsilon fraction of corruptions, even in the weakest models that I described in the Huber model, is going to require error omega of epsilon, some constant times epsilon, which I'm not going to bother to calculate what it is, but I'm going to tell you what it is. So what's the idea for that? The idea is that if you have two distributions, P1 and P2, okay? Actually, I should move here, there's no reason to. That have total variation distance about epsilon, okay? Then you can always find noise distributions, B1 and B2, such that the noisy version of P1 in Huber's model, so 1 minus epsilon P1 plus epsilon B1, is identical to the noisy version of P2. Okay, so there is a way to add noise, different type of noise, to each one of the two, so that the noise distributions are identical. Therefore, it's impossible to distinguish between them, even in the infinite sample regime. So how do you do that? Well, what does it mean that P1 and P2 have total variation distance that? It means that there is some basis distribution P, such that P1 is 1 minus the different times this P, plus the rest times some other distribution. This is Q1 for P1 and Q2 for P2. So what do we do since P1 and P2 look like that, given that we want to make the noisy distributions be the same? So what noise am I going to choose for P1? And so what's going to be B1 and what's going to be B2? So we want to achieve this identity. So the noise you're going to get for B1 is going to be Q2, which is basically the added term for P2. And the noise you're going to choose for P2 is the symmetric. Okay? So you can do the calculation like nothing deep is happening. So the message is that there is a way to corrupt each one of the two, so that the two corrupted distributions are identical, therefore you cannot distinguish between them. Now, how does this translate to learning the mean of a Gaussian? Well, the only thing you need to understand is what's the relationship between the total variation distance between Gaussians and the Euclidean distance between the mean vectors. In this case, we have one dimension, so just the absolute value between the means. So literally what we're going to do is we're going to take Pi to be some Gaussian with some mean vector and identity covariance, and we're going to apply the previous claim. Okay, so total variation distance between P1 and P2 being this one really means that the distance between the means in absolute value, these are numbers now, it's going to be at least a constant times epsilon. Okay, so that's the proof. And if you care about the constant, then you can do it. It's going to be something like square root pi over 2. Okay, so that's the constant for actually estimating the mean in one dimension. Now, one important thing that I should say here is that this omega of epsilon error, when you have an epsilon fraction of corruptions, is just a coincidence of having Gaussian distributions. If you have a distribution drawn from a more general family, for example, a sub-Gaussian, the answer would be some other function of epsilon. If you had some bounded moment condition, again, Okay, so you need to calculate what the information theoretic optimum is going to be based on the assumption you have about the good data. All right? Any questions so far? Okay, so let me move on. So the next thing I'm going to show you is that if you don't care about running time, you can solve the problem. Okay, there's an algorithm that uses a few samples, runs in time exponentially in the dimension, and robustly estimates the mean within the information theoretically optimal error, again up to a constant factor, for the Gaussian. In fact, if you see the proof, this is not only for the Gaussian, it's for more general distribution. So what's the idea? Is the statement clear? Okay, so let me parse it. So there is an algorithm, so computationally inefficient algorithm, that uses d over epsilon square corrupted samples. This sample is going to be corrupted samples from a Gaussian with identity covariance and a known mean vector, and outputs a hypothesis mean vector, so a mu tilde in R to the d, such that with high probability over the samples, the Euclidean distance between the estimate and the true mean is a constant times epsilon. So this is what we'd like to prove. So how would you do that? Are there any ideas? We said that the empirical mean doesn't work, right? And the coordinate-wise median doesn't work. A bunch of things don't work. But if you try to see what all these algorithms are doing, that they're trying to reduce the high-dimensional problem to a collection of low-dimensional problems. So the coordinate-wise median says, okay, I can solve it in one dimension. Let's try to do it independently for all the dimensions. This idea works, but it's a little bit more complicated. Unfortunately, in general, you have to look at exponentially many one-dimensional problems. So this is not something that should be unusual for computer scientists. We just use random projections, or maybe all possible projections. So the idea is to just find, to robustly estimate the mean of all the one-dimensional projections. This was Tukey's idea. Okay, this is what the Tukey median actually does. So the very basic fact we're going to use here, which is sort of a tautology. The reason I'm pointing this out is because when you want to robustly estimate more general quantities like covariance matrix or more general moments, something like that should be your starting point. What does it say here? We take any vector, its L2 norm is the same thing as you take the maximum inner product with any unit vector. Okay? So take all projections on unit vectors, take the maximum of the absolute value of the inner product. That's what this says. So this gives us an algorithm. So the claim is, suppose that, so this is going to be an infinite time algorithm so far. Suppose that we can estimate, so mu is what we're looking for. Okay, it's a vector in d dimensions. Suppose that for every direction v, we can estimate the inner product of v and mu. Okay, let me call this mu hat v. Simultaneously. Then the claim is that we can patch those estimates, those one-dimensional estimates together, and estimate the vector mu within error, which is basically twice the error we get for the one-dimensional problem. So this is just a reduction of the high-dimensional problem to infinitely many one-dimensional problems. Is it clear? So how do we do that? Well, I'm going to formulate an infinite-size linear program. So what's going to be in the linear program? So the variable is going to be a d-dimensional vector. Ideally, this should be the mean that we're looking for. This should be mu. This is the intended solution. And the constraints are that for every unit vector in d dimensions, the absolute value of the difference between these one-dimensional estimates that somehow you have computed and the dimension times the variable is less than or equal to delta. Okay, that's a linear program, all right? The variables are x, so you have infinitely many constraints. So the first observation is actually a feasible linear program. Yes?
So is it obvious that there's a unique mu, in other words?
It is not. It is not, and there is no unique mu, but it doesn't matter. The next, yeah, it doesn't matter. The next, because I want to estimate the truth within some small distance, right? So, okay, so the first observation is, as Ravi said, there is no unique solution, but we're going to show that any feasible solution to this LP works. And this LP is feasible. Why? Because the true mean actually satisfied it by assumption. We have assumed that these numbers we have calculated, these mu hat v's, actually satisfy this LP. Okay, so for these numbers, the true mean satisfies this LP, so it's a feasible LP. And the claim that to take any feasible solution, then it works. So, okay, what am I going to do? I'm going to look at the Euclidean distance between any feasible solution I take and mu, which is what I'm looking for. By definition, this basic fact is going to be the maximum of these inner products. I'm going to use a triangle inequality, and in the middle, I'm going to put mu hat v for every particular v. So I get the sum of these two terms. And the claim is that each one of these two terms is at most delta. Okay, why? Because x star is a feasible solution to this LP, not necessarily the same as mu, so it satisfies that this maximum is less than or equal to delta, and mu is also a feasible solution, so I get another delta. Answer to delta. So claim proved. So very basic. Now, of course, this is not an algorithm. It's you need like an infinite number of inequalities, but a small tweak tells you, which I'm not going to show in detail, that if you do the same calculation by taking not all possible directions, but a gamma net under L2 over all directions, the same thing works. In particular, if you do that, so let's say C is a gamma net over all directions, which means a set of vectors, that every other vector is within distance gamma in Euclidean distance, all of them units. So how many inequalities do I have now? I have the size of the net. I have one inequality for every vector in C. So I have something like 1 over gamma to the d, many inequalities, and gamma is going to be constant at the end. So you can see here that if I do that, then the error I'm going to get is not going to be 2 delta, as it was in the previous slide. It's going to be 2 delta divided by 1 minus gamma. Let's take gamma to be half. So overall, I get that with a program that has 2 to the O of d many inequalities, I can solve the problem. Okay? So, yes?
So it's a little better than the n to the d.
Yes, it's better than n to the d. So let me tell you about sample complexity now. So far I haven't used the median anywhere. The only thing I used is that for every one-dimensional projection, I can robustly estimate the mean of that projection. So the median satisfies that, and this delta would be a constant times epsilon with high probability. So I need the high probability statement. So the sample complexity would be something like 1 over epsilon squared times log 1 over the error probability, as was asked before. So I'm going to take the same sample and apply union bounds. So how small should tau be so that this works? Well, it has to be at least 1 over the size of the, at most 1 over the size of the cover, which basically gives us by union bounds that, if you do the calculation, that, so this is going to be something like 2 to the d, so you get d over epsilon square samples. So with d over epsilon square samples with high constant probability 99%, any feasible solution to this linear program is going to be 4 delta accurate, so O of epsilon accurate. And the running time of this thing, as David said, since you have 2 to the d size LP, is going to be polynomial in n and 2 to the d, and the polynomial in n you need it because you actually need to solve the one-dimensional problem basically 2 to the d times. So every time you need time n. So that's the algorithm. So if d was small, we would be done. But unfortunately, we're not happy with an exponential time algorithm, so you have to do more. And again, the point is that this type of generic idea doesn't only work for the Gaussian. It always works as long as we have a good robust estimator in one dimension. Of course, the error wouldn't be epsilon, would be of delta for whatever that delta is. Okay, so it seems I'm a little bit over time. So let me move on. So the second basic thing I wanted to say is about, or the third, maybe it's about outlier detection. So what does it mean to remove the obvious outliers? So let's do an experiment here. So these are a bunch of points from a spherical Gaussian. Can someone tell me what the outliers are? Madhu. So is this point an outlier?
Sure.
This, this, and this inside, right? So these are the outliers. That makes sense. So all these points are certainly outliers. But these are not the only outliers necessarily, and this is the problem. These points could also be outliers. And there is no way to eyeball them, and this, just by looking at the points and deciding that individually each one of those red points here are actually outliers. And these are the outliers that cause the epsilon to become epsilon root d in the output. So the whole effort algorithmically is to actually find those guys and remove them, or at least eliminate their effect to some extent. Now, naive pruning, this naive outlier removal I mentioned before, it's just a method of removing these guys that are further out or inside, and it's justified by this Gaussian annulus theorem that Ravi mentioned on Monday. We know that the spherical Gaussian, let's say with identity covariance, if you look at the length of a sample, it's going to be very close to root D with very high probability. So it's extremely unlikely, even if you take many samples, that you have samples that are either outside this thin shell, inside this thin shell, or outside. Okay, so this is a basic fact that we're using, the global concentration of the data, that allows us to remove some basic outliers, but it's not enough. Okay? We know much more about the data set and about this concentration, and we need to exploit it to design actually robust algorithms. Okay, so I think this is the last introductory slide. So for the algorithms I'm going to describe, it's very useful to think what happens in one dimension. So what happens to a one-dimensional Gaussian when I add corrupted data and when I subtract corrupted data, as long as I add or subtract at most an epsilon fraction. So let's look at mu1. So this is what it is. Suppose I subtract an epsilon fraction of the data. So you can think of that as being similar to removing an epsilon fraction of the probability mass from the distribution. Okay? In the limit, these two operations are the same. So what is the worst, I guess I'm writing it here. So what's the worst effect on the mean you can have by removing an epsilon fraction of the mass from a Gaussian? You have to remove it from one of the tails, right? And by Gaussian concentration, this is going to move the mean by at most epsilon root log 1 over epsilon, because we know that the tails are at this distance from the true mean. And the effect of the variance would be similar. So we cannot increase it by too much by removing points. We can increase it by at most epsilon. Why is that? If we remove an epsilon fraction of the mode, it's very, very close to the mean. Then by rescaling, it's going to increase by epsilon. But we can decrease it more substantially. We can decrease it by at most epsilon log 1 over epsilon. How? How can I decrease the variance? Again, remove one of the tails. This decreases the variance by epsilon log 1 over epsilon. It's just another calculation. On the other hand, for additive errors, things are can be more extreme. If you add even 1 point, this can move the mean and the covariance arbitrarily. Okay, just move it here. So this is why the empirical mean doesn't work. And again, the variance can increase arbitrarily, cannot decrease too much. It can decrease by at most epsilon, which happens if you add all the points here. All right, so these sort of rules of thumb are essentially the basis for the high-dimensional algorithms I'm going to describe. So whatever is true in one dimension, the obvious generalization holds in high dimensions. So are there any questions about this slide? Okay, so let me move on. But basically, try to remember these things. Okay, this is the only thing you need. Then whatever is true in one dimension is true in high dimensions as well. Just requires a little bit more effort to prove. So let me give you an overview of these algorithmic approaches. So there are 2 or 3 I'm going to describe. The high-level goal of every algorithm that learns high-dimensional data that has low-dimensional structure is somehow to reduce the problem to a bunch of low-dimensional problems, solve each low-dimensional problem, and then combine. Okay? Now, there are various ways to do that. So the way that the LRV work does it is somehow reducing the dimension of the problem by a factor of 2 in every iteration. So you solve many problems in lower dimension. And the way that the iterative filtering and soft outlier removal of the work I have been involved in does it is different. So basically, what it does is that iteratively finds and removes outliers until we're left with a set of points such that the standard estimator, the empirical mean, works. So all these algorithms are essentially spectral in the sense that they look at the spectrum of the empirical covariance matrix, and based on that, they can robustly estimate the mean. Okay, and this is a general phenomenon. In order to be able to robustly estimate some moments, you have to look at higher empirical moments, and based on the structure of those, be able to say something. Okay? So the first technical parts of the talk is going to be this thing that we call certificate of robustness. What does this mean? So even when we have corrupted data, it's quite possible that the standard estimator, the MLE, or in particular the empirical mean, works. Okay, there is no reason to believe that it doesn't work a priori. It might work. So we want to understand when it works. And the first idea here, which is present in both works, so remember this slide and all the slides that are like that. If the empirical covariance is close to what it should be, then the empirical mean works. Okay, so if the second empirical moment is what you would expect it to be, if there were no outliers, then the empirical mean, so the first empirical moment is actually close to the true mean. And this is the picture, which is similar to what I had before. So we have a spherical Gaussian, and you have these points here that are in one, let's say, direction or lower dimensional subspace of the spherical shell where all the samples are concentrated. So if there is no direction where this empirical covariance metric has large variance, then the empirical mean works. So the only way that the empirical mean is far from the true mean is if the covariant matrix, which should be spherical, has become elliptical in some sense because of the corrupted data. And the only way it can become elliptical is if a decent fraction of the corrupted data will actually collude to move it in some specific directions. It doesn't need to be one direction, this is just an illustration. You can have many orthogonal directions or non-orthogonal when this happens. But the point is there has to be a large eigenvalue of this matrix, and we don't expect that such an eigenvalue would exist without corruptions. Now the lemma, and I'm going to try to actually prove in the next 7 minutes, I think it's not going to happen, is this. So it says the following. So let's take n epsilon corrupted samples from a standard Gaussian with a known mean vector. Let's form the first two empirical moments. So these are formed based on the entire set of samples. So they contain both corrupted and uncorrupted samples. And these are things we can observe. Okay, we can find mu hats. We can find sigma hat. So this is what mu hat and sigma hat means in this slide and the next few slides. Then, with high probability over the good samples, if the spectral norm of the empirical covariance matrix is at most 1 plus epsilon, then the distance of the empirical mean from the true mean is at most epsilon. So this is what LRV shows in the additive contamination model, where the adversary can only add corrupted data. And what we showed is that if the left-hand side, the spectral norm of the empirical covariance is at most 1 plus epsilon log 1 over epsilon, then the distance is going to be epsilon root log 1 over epsilon. Now both these lemmas are actually optimal. The parameters are optimal. Let me show you why. So these are the actual implications. So if you don't have a epsilon, the left-hand side you have some delta, some positive number. Then the right-hand side in the additive model would be square root of the product of delta and epsilon plus an epsilon. So even if delta is equal to 0, you cannot avoid the epsilon on the right-hand side. And for the strong model, the delta in the left-hand side, the delta deviation in the spectral norm of what you would expect becomes, again, you get the same square roots, but instead of epsilon, you get something bigger. You get epsilon times square root log, and these are the things that ideally we would like to prove. Okay, so this is part one. So I have maybe 5 minutes for this hour. So maybe I'm going to show you how we prove it for the additive case. The proof is really easy if you believe some calculations, okay, which anyone in this room can do. So let's recap the theorem. So we are in the additive model. The adversary can only add corrupted samples. The empirical mean mu hat, the empirical covariance sigma hat in d dimensions. The assumption is going to be that the spectral norm of sigma hat is going to be at most 1 plus delta for some positive delta. The conclusion is going to be that the Euclidean distance between the empirical mean and the true mean is going to be at most that. Okay? So how do we prove that? Well, we just write down the empirical mean and the empirical covariance, and we express them as a function of the good samples and the function of the corrupted samples. This is what we get. So let's say S is our initial set, the set of additively epsilon corrupted points. So, and let's assume without lots of generality that the true mean is 0. Everything we do is translation invariant. Then we can write S, again, S is the set of epsilon corrupted points, so it means it contains a 1 minus epsilon fraction of good points and an epsilon fraction of bad points. Okay? So these points in G are IID Gaussians. Okay, in fact, N0I, because I assume that mu is 0. And the rest are arbitrary. I don't know anything about them, but I know that the size of B is epsilon times the size of S, so it's at most an epsilon fraction. So I just write down what the empirical mean is going to be of the entire data set as a function of the empirical mean of G, the empirical mean of B, the empirical covariance of G and B. So mu hat G is going to be the empirical mean of the good data. Okay, you sum all the good data, you define it by their number. Yes?
Sorry for a quick interrupt. If mu and mu hat are very far, then the good guys will have very high variance with respect to mu hat, and that kills you, isn't it?
Yeah, what I'm going to show that. That's a proof, the proof is easy. Okay, so mu hat G is the empirical mean of the good data, mu hat B is the empirical mean of the bad data. And I know that the size of G is 1 minus epsilon times n, and the size of B is epsilon times n. So I can write, that basically I can assume that the number of samples goes to infinity for simplicity. So I know that mu hat G is going to converge to its limiting value, which is going to be the true mean, which is 0. So under this minor assumption, I get that the empirical mean of the entire data set is going to be an epsilon fraction of the empirical mean of the mu hat B. So the only way that this mu hat is large is this mu hat B is very large. And we're going to show that the only way that mu hat B is going to be very large, in fact, if we have the right contribution to the covariance. So this is claim 1. This is what you need to remember. Actually, I think I repeated here. Assumption, the true mean is 0, and the empirical mean is epsilon times the empirical mean of the corrupted points. And I can do the same calculation for the covariance. I'm not going to show you how we do this, but this is what we get. Okay, this is just like a one-dimensional, essentially, calculation. So what does this say? The empirical covariance of the entire data set is going to be 1 minus epsilon fraction times the empirical covariance of the good points. But the empirical covariance of the good points is going to be essentially identity because I get many samples. And then I have a contribution from the empirical covariance of the bad points, and a contribution of this rank 1 thing, which is this matrix obtained by mu hat B with itself. Okay? So I claim that based on these calculations, we're done. Okay? If you believe this claim, then we're done. So why? So these are the things that we have. Okay? So recall that the spectral norm of the matrix is just this quantity, this maximum of V transpose sigma V. Okay? So, and because we know that sigma hat looks like this, okay, we know that this matrix here is positive semi-definite, identity is identity, and this is a rank 1 thing. So this is V transpose sigma hat V for every vector V. So there is a 1 minus epsilon contribution from the identity, some non-negative contribution for sigma hat B, and something else that comes from mu hat B. So I just need to choose a vector V that maximizes quantity, and then I'm going to get like a lower bound on the spectral norm. What V should I choose? So it has to be in the direction of mu hat B, right? So take a unit vector in the direction of mu hat B. Because this thing is going to be non-negative, this thing is PSD, so I get that the spectral norm of sigma hat is going to be at least 1 minus epsilon plus roughly epsilon times the L2 square norm of mu hat B. And from that I just do a manipulation and get that if this thing is small, then this thing is small, and therefore the L2 square norm of the bad point mean vector is going to be bounded by 1 plus delta over epsilon. And because I know by claim 1 that the true mean vector is an epsilon fraction of that, I get that the difference between mu hat and mu is exactly the same as the L2 norm of mu, because I assume that mu is 0. L2 norm of mu hat, and the L2 norm of mu hat is epsilon times the L2 norm of mu hat B. So by the above line, I get my implication and I'm done. Okay, so that's the end of this lemma. And I think at this point I'm going to, I think I'll take maybe a question or two and we'll take a break.
What happened to the middle term?
Which middle term? This one. Sigma hat B is a covariance matrix. It's positive semi-definite, and therefore this term is always going to be non-negative. And in fact, the worst case is to put all these bad points in a multiset concentrated on one location, and therefore this thing is going to be 0, so this is going to be 0. This is actually tight. Yes?
So it seems that this approach fundamentally depends on knowing the true covariance matrix a priori. Is that the right intuition?
No, it doesn't. Okay, this is for the purpose of this illustration. So these results have been, what I've said so far, yes. But these results can be generalized even for unknown covariance and robustly estimate higher moments, etc. What you need to know is you need to know something about the higher moments of the distribution of the good data. Okay, but it's a reasonable assumption based on what you've seen so far. Any other questions? Okay, so I guess let's take a break and resume at 3:30.